Let's see here how we are going to work with the problems from chapter 25. Okay, then this is really here the second part where it was deleted accidentally, and I'm gonna go over it again. For the first problem here, it has to do with the calculation of currents. And here I have copper that has 8.5 10 to 28 free electrons per cubic meter. And this is the lowercase n. And I have the length of it as 1.0 centimeters. And here this is something from the industry, a 12 gauge copper, and it is translated to the diameter as 2.05 millimeters. And it has a current that is going through it, which is 4.85 amperes. How much time does it take for an electron to travel the length of the wire? Repeat part A for 6 gauge copper wire, which is a diameter of 4.12 millimeters of the same length, and it has the same current. And generally speaking, how does changing the diameter of a wire that carries given amount of current affect the drift velocity of electrons in the wire? As I said, this is n, lowercase n. It is the number of electrons divided by the volume. This is not the speed. And this is 8.5 10 to 28. And this is electrons per cubic meters. And I have L converted into meters, 0.710. And I is 4.85 amperes. And this is the radius. We have the equation as I equals NdA times QE, which is the electronic charge, which here I will use 1.602 10 to 19 coulombs, negative 19 coulombs. Vd here, the drift velocity, it is I divided by NA, a q of the electron, and then I was able to calculate the drift velocity. And then we're assuming that the drift velocity is constant. Then here T is going to be the length of the wire divided by the velocity, and this is going to give us 110 minutes. I can repeat the same exact calculation, but using the proportionality between the time and r squared. And from that, I can really get that when D is the diameter, which is 2R, I can find that this is the relation. And then this is really the 440 minutes time is going to be 4 times. Here I have 1.50 meter cylindrical rod of diameter 0.5 centimeter is connected to a power supply that maintains a constant potential difference of 15 volts across its ends. While an ammeter measures the current through it, you observe that at room temperature, which is assumed to be 20, the ammeter reads 18.5, while at 92.0 degrees Celsius, it reads 17.2. You can ignore any thermal expansion of the rod. And we want to find the resistivity at 20 and the temperature coefficient. Okay, here I have L as 1.50. D was given as 0.5 centimeters. Then I need to calculate R, and I would say the voltage is 15 volts. At 20 degrees Celsius, I1 was 18.5, and at 92, I2 was 17.2. I know that I equals V over R1, and R, like these are the equations that I'm going to use, and this is R equals rho L divided by A. Also, like R, its dependence on temperature. All right, and therefore I will say I'm gonna solve first for what is really rho, which is the resistivity here after I have calculated the resistance as voltage divided by current. And then I will be able to calculate what is really the resistivity. And then at 92 also, like I have the voltage, which is the same, and I have I different, then I will be able to calculate what is really R. And then R, its dependence on temperature, it is given by this equation. I have calculated rho, and therefore I will be able here to calculate, you know, I was able to calculate rho, and then I will be able here to calculate R. And from that, I will be able to find out what is going to be alpha. Okay, here we have simple circuits, and like with the switches and how they're gonna behave. Then here, when the switch here is open, the voltmeter reads 3.08, and this is actually when I wanna measure the EMF. Then like I directly, I can say that this is the VO, which is the EMF equals 3.08. When the switch, of course, is closed, then there is a current that is really going through the internal resistance, and therefore the reading is going to drop to 2.97 volts, and the emitter reads 1.65. And then the first question I have answered, find the EMF, and then the internal resistance. I can use VAB equals EMF minus IR, and equals 2.97. Then I can use this to calculate the lowercase r, which is the internal resistance of the circuit. Of course, also I can use Ohm's law to calculate what is the value of the resistor R, because you know, the potential difference here across R, it's the same, which is the 2.97, and therefore R equals VAB divided by I. Okay, this one here, it is again related to circuits that they have only one path. And here I have the circuit contains two batteries, each with an EMF, an internal resistance, and two resistors in the circuit. Find the current in the circuit, magnitude and direction, and the terminal voltage VAB of the 16 volts battery, and the potential difference VAC of point A with respect to point C. And I will, you know, this picture, it is from your textbook, where we're gonna show how really the voltage drops across the circuit. We're gonna do the same for this circuit. Now with circuits, I will say always we are going to assume a direction, either clockwise or counterclockwise. And if after doing the calculation, the current is going to be negative, then it should be the opposite. Then here, when I will say I'm going to consider sweeping the circuit counterclockwise, I know that when I will, you know, go in the circuit through from B to B, the VBB is going to be VB minus VB equals 0. Then when I go to the same point, I will have that 0. Now, any time, it's very similar to you know, going all the circuits is going to be the same. When I go through the 16 volts, I will go from low to high, then the drop in the voltage is going to be positive, 16 volts. And for the resistor, when I go in the direction of the current, is going to be negative. Negative here, I, because I have only one current through the circuit, times the value of the resistor, which is 1.6 ohms. And then here also, I will say minus I 5.0 ohms, minus I 1.4, And then I'm gonna continue through the circuit. When I will reach the second EMF, I am going from positive to negative, then I have negative 8 volts. Now, the only unknown in this equation is I. I will collect the terms, and then I is going to be, the 8 divided by 17, which is 0.47 amperes. B, if I will calculate VAB, I will go this is going to be from, going from B, 16 volts, and then negative 1.6 ohms. And that is going to be 15.2 volts. I believe this one not this equation. I thought this is the one, I thought there is one that I have a mistake in. VAC, it's the same way, and it came up to be negative 11. Now, when I will go here to draw, okay, when I go from B, which is here, to here, okay, I'm gonna go up 16. This is 16 volts. And then there is a wire, and that wire is gonna be the value when it is constant. And then because of that 1.6 ohms, I'm gonna have a drop, which is 0.752. This is actually calculated based on the current times the value of the resistor. And then because I have a wire here, this is a wire, then it's gonna stay stable at a certain time. And then it's gonna drop because of the negative 2.3, and you can continue with the voltages, and finally you are going to reach the same level where you were in when you were at B. Now, this is the last one. When a resistor with resistance R is connected to a 1.50 volt flashlight battery, the resistor consumes 0.0625 watts of electrical power throughout. Assume that each battery has negligible internal resistance. What power does a resistor consume if it is connected to a 12.6 volts car battery? Assume that our voltage remains constant when the power consumption changes. Okay, and therefore I will say here, I'm gonna use for the power, I can use I squared times R, and I can derive the other one because this is the only one that I memorize. Then it's gonna be V squared over R equals 0.0625 watts. From that, I will be able to calculate what is the value of my resistor, which is 36. Then I will be able to calculate the power based on the voltage is going to stay the same. Then it is V squared over R, and that is going to be 4.41 watts. And then if I wish to calculate the voltage when the power is 5, it's again the same formula, and I will take the square root and I will find that V is going to be 13.4 volts. Thank you and have a great day. I hope that this video is going to be okay.